All right, here was a couple warm-ups for you to do using substitution. Let me give you a minute or two to do them, and we'll do them together. In case you're missing how to start the first one, I would switch that to sine x over cosine x. You'll find when you're going through some of these longer problems that a lot of the work that's eating up most of the time in paper is not calculus. It's just algebra. It's manipulating shit and writing it into an easier form. Or you're doing calculus is extremely fucking hard. But if you're working smartly, you're using your algebra skills to manipulate stuff to make it easier. Right? Hopefully you went with like u equals cosine x. So du equals negative sine x dx. Did anyone try to use sine x and take the use u as sine x? It's a natural thing to want to try. But when you take the derivative, you have cosine x, but in the integral, cosine x is in the denominator. It's not in the numerator, so it's not a swap. They don't cancel out. So if I divide by negative sine x here, 1 over negative sine x du equals dx. And I have sine x over u times negative 1 over sine x du. So I just get the integral of negative 1 over u du. Matthew, you're walking by. He's got his head in his phone, autopilot down the hall. What?
Reading the return policy.
What do we take the derivative of that would give us 1 over u? What? Ellen, yeah. I'm gonna move the negative outside so that we're just doing the 1 over u. Ln of u is what it is. It's gonna be absolute value of u, just to make sure. And then we have our constant of integration. What should I substitute over here? Natural log x. In this case, doing the denominator doesn't help. If you did the denominator, you'd have x to the negative 1, and you take the derivative, it's negative x to the negative 2, and we don't have anything like that. But here we have du equals 1 over x dx, and we actually have a 1 over x. So I have, and I'm going to rewrite it as I would normally write it. But every once in a while you see people in books write the 4 here like it's sine or cosine. And then I'm going to put the 1 over x over here with the dx and show that this is my du. And this is going to be u to the 4th. So I have the integral of u to the 4th du. And what's the integral of u to the 4th? U to the 5th over 5. Or you could put the 1/5 out front plus c. Are we good with that? Is everyone happy with our answer? Is there anything that should change? Madeline? Yeah, I didn't do it in either one. I wanted to see if anyone would say anything, but yeah, we didn't start with u. We can't end with u. So here u was cosine x, so this is going to be negative natural log of cosine x plus c. And this is going to be 1/5 natural log of x to the 5th power plus c. Good. So don't forget to get rid of u and put back your original thing in.
Substitute.
The x in the denominator went away with the du dx. So our u did not have a 1 over x in it. U was just natural log of x.
Right.
So when I put u back in, I'm just replacing u with natural log of x. The 1 over x was eaten. This is du equals that right there, and we had that right there. So I took that block out and I put in du. Does that make sense? Any other questions? All right, let's take a look at chapter 5.4. Five point four is on sigma notation. So we could have sigma k equals 1 to 4 k squared. That is capital sigma. In mathematics, its official definition is add shit up. Well, that's Hefe's official definition of it. The letter that is listed below sigma is called the index. Anything will work, but the most common ones are I, J, K, and N. Those are the most common ones you see. The number that it starts with, or the number on the bottom, is what it starts with. Start with this number. And the number on top is the number we're going to end with. So what it means is take that number, plug it in, and iterate. Go to the next number up. The next number up would be 2. I'm going to plug that in, and it's squared. And I'm going to keep doing that until I get to the number on the top. And if I do that, I've got what? 1 plus 4 plus 9 plus 16. I got 30. So it has a value. It actually equals a sum. We added the shit up. Common starting values are 0 and 1. Those are the most common ones. But they don't have to. Zero, because we generally say initial time is t equals 0. So if we're doing something with time, we might start with 0. And then 1, because it's our first countable number. And many of the formulas start with this index. Formulas start with 1. We'll see some formulas today. Does what I did here make sense with that right there? If anyone doesn't understand it, you got to say something now. It's that simple, Isaac. It really is. So where's the catch? This is too easy. I'm glad that you feel it's simple. This isn't really kicking it up a notch. Let's start with I equals 0 to 5 and do 3i. Why don't you guys go ahead and do that one? This is pretty straightforward. Alright. So hopefully you got 3 times 0 plus 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. Oh god, that was a lot of writing. What do I got? 0 plus 3 plus 6 plus 9 plus 12 plus 15. 18, 18, and 9, 45. Let's see, 30, 45. Yeah, I'm getting 45. That was a little tedious, wasn't it? Feels like we could maybe like simplify this a little bit. Maybe factor out the I there. Add them up, then multiply by 3. It's factoring, that's just algebraic factoring. They all have a factor of 3, you know. Let's see. 1 and 5 is 6. 4 makes 10. 10 and 5 is 15. So we got 3 times 15 is 45. Right? But this 0, 1, 2, 3, 4, 5, this bit right here, that's just I equals 0 to 5 of k. Or I, sorry. And the 3 is on the outside, like that. Let me write that where it looks cleaner. There we go. So scalar multipliers, that's what they're called, scalars, or the constant multipliers can be factored out. Outside the summation. Any questions? You're like, where's the calculus here? This is leading to one of the most important things in calculus. So, some basic algebra shit. And let's be honest, the thing we did for 4 fucking chapters, derivatives, was based on f of x plus h minus f of x over h. A simple algebraic formula. So a lot of this calculus is based on algebra. So we're getting there. This is just a new notation that you may not be familiar with, depending on who you took college algebra with. All right, what about n equals 1 to 5, 1 over n? This is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. I'm not going to make you clean that up. Some things aren't easy to simplify, but in Calc 2, you start exploring stuff that uses this. These harder things, you'll start exploring them. These, when we add a bunch of terms up, is called a series. Now, you'll hear that again in Calc 2. This is different than a sequence. A sequence would be 1/1, comma 1/2, comma 1/3, comma 1/4, comma 1/5. A series adds up shit in a sequence. So you're going to come back to that in Calc 2. I think it's Calc 2. I think. Sure as hell is in Calc 1. And I know it's not Calc 3. And I'm pretty sure I learned it at COS. So we're running out of upper division math courses for it to be in. Doesn't fit in linear. It's got to be Calc 2. It doesn't fit anywhere else. What about something like n equals 2 to 2 of 5n to the third power? Cody's over here saying it is Calc 2. It's all definitive about it. I guess I could look through the textbook and see. It'll say sequences and series. It's probably chapter 9 or so. There's only one n though, right? It starts at 2, it ends at 2. This is just 5 times 2 cubed. 5 times 8 is 40. There wasn't a bunch of shit to add up. Next one, and has a little learning lesson in it. Well, that's my k equals 1 term. My k equals 2 term. My k equals 3 term. K equals 4 term. K equals 5 term. K equals 6 term. And what I end up, if I add all those up, is 18, which is 3 times 6. So something nice little falls out. There's a little formula to be garnered here. If we have k equals 1 to n and a constant here, it's just the constant times n. Whatever is that's assuming k starts at 1, of course, or 0. It could start at 0 here and it doesn't change it. Wake up, Matthew. Right, you're getting drowsy.
Got a full night's rest, I don't know what's up. Right?
What's the answer here? 20? 20x. The answer here is 20x. This is constant with respect to k. So we just do c times n, where this is 5x and that's 4. It's a trap. All right, let's take a look at a summation that doesn't start at 1 and how we can go about rewriting it. N equals 3 to 5. Let's go with 2 to the n minus 1. Well, this would be 2 to the 3 minus 1 plus 2, 4 minus 1 plus 2 to the 5 minus 1. This is 2 squared plus 2 cubed plus 2 to the 4th power. Whatever we do, we need to end up with that. So let's re-index with k equals 0. So this is here is an easy way to go about doing this. I've got k equals 0 and I've got n equals 3. I want to rewrite this so that the right side equals what k equals. Equals k. In this case, it would be subtracting 3 from both sides. I have n minus 3 equals 0. And now with both of them equal to 0, I can set them equal to each other. K equals n minus 3. And that also means that n equals k plus 3 if I add 3 to both sides. what does this do to my indices? Indices is plural for index. When n equals 0 or n equals 3, k equals n minus 3. So 3 minus 3 is 0. And when n equals 5, k equals 5 minus 3 is 2. We will rewrite this from k equals 0 to 2. And now here, there's a reason why I rewrote n in terms of k's. We have 2 to the n minus 1. I'm going to take this n and replace n with k plus 3 in the formula. So that would clean up to k equals 0 to 2. K plus 3 minus 1, we don't need the parentheses. So k plus 3 minus 1 is 2, so k plus 2. Do we still get the same sequence or series? 2 to the 0 plus 2 plus 2 to the 1 plus 2 plus 2 to the 2 plus 2. 2 squared plus 2 cubed plus 2 to the 4th. Which is what we had up here. So that has been re-indexed k equals 0. If I wanted to do re-index to k equals 1 instead, I would have had n equals 3. Subtract 2 from both sides, and I get n minus 2 equals 1. And now I could say k equals n minus 2. And we would start at 1. We would have the summation from k equals 1 to 3. And 2 to the k plus 1. So that's a little bit of how to re-index. Yeah, press.
So do we need to like always reindex or reindex, or can we just like, if we can just read it, can we just do it like that? Like for the ritual?
Yeah, but you're gonna see, like, coming up in a second, we got formulas that you do not wanna do from a different index, like, and it requires starting at 1. And big picture, you won't do this a lot. Because remember what this chapter was on. Integration. So this is somehow going to lead us back to integration. You guys ready? Yeah, Matt.
So when you first re-index K0, set K0, in the second one, you did K1, set equal to K, and minus 2. Where we did that?
Right here. The K started, we want K started with 1, N started with 3. I want to rewrite this so that the right side has the same value as 1. I want this to equal 1. So I can make it K. And so I subtracted 2 to make it 1. Huh? It tends to be easier to see when it's 0, because we do that with factoring and stuff. But like doing it to a different index, a lot of students get hung up. All right, let's take a look at some formulas. I'll prove one of them. We actually kind of did something similar with this first one. K equals 1 to, I don't know, N, yeah. Of C times A to the K is the constant times K equals 1 to N of AK. Example, look at the 3i one we did. I'm actually going to show 2 of them, prove 2 of them. Because the next one is like this, what we do in it, you actually, if you realize and pay attention to how it works, you'll be able to repeat it on a lot of stuff in future classes. So to show how this works, just start writing it out. I got A1 plus B1 plus A2 plus B2 plus A3 plus B3 plus ... plus AN plus BN. Everything here is being added together. There's nothing being multiplied. There's no need for the parentheses. So I got an entire sequence or series of terms being added together. What can I do with things that are added together? I can rearrange them and it doesn't change the property or the sum. The commutative property of addition says I can regroup these as this. So I just rearrange the terms. Those are my A's, these are my B's. This here is the very sequence K equals 1 to N of AK. And that is k equals 1 to n of bk. And the plus sign in between them is all that we needed to show it. Some other ones. If I do k equals 1 to n of k. It's called the closed form. And I assume that's the open form. We'll prove this one in a second. Sum of k equals 1 to n of k squared. These are a lot less fun. That's the condensed form. This is 1 squared plus 2 squared plus dot 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 plus n squared. It feels like I have an extra n there. Maybe not. No, one of the n's goes away in division. And then the cubic one. Let's take a 5-minute break. Someone just went to the bathroom. Preston's going now. And it's about that time. I was going to wait till after. Let's take a gander at proving this first one here. I hope the one we did here, learning how to like write the terms out and rearrange them is a helpful skill you'll use later on. This next one is kind of like some magic bullshit. You're going to call bullshit when I do it. Well, not bullshit, but like, there's no way I would have come up with that. We're doing the sum from k equals 1 to n of k, and we're going to show that it equals n times n plus 2, or n plus 1 over 2. Proof. start out, just write it out. And now this is where the bullshit begins. I'm gonna do the same thing. And I'm gonna write it out in reverse order. So I've got n. This would be n minus 2 plus n minus 3. Add them up. If I add these up, I have 2 of the summations on the left. On the right, I'm just gonna add vertically. I've got n plus 1 there. And I add these 2, and I've got another n plus 1 there. And I add these 2, and I have another n plus 1 there. And I keep doing this. And I got n plus 1 there. And finally, another n plus 1 there. How many of these are there? N, because we did 1 to n, we did n. So right now we're looking, I'm gonna rewrite that as multiplication rather than some adding. And now you can, oh, I'm missing a k in here on all of these, like a fucking scrub. Finally, we divide by 2. Or effectively multiply both sides by 1/2. The sum of the first n numbers is n times n plus 1 over 2. There's a story about who this happened to. I forget who though. Young kid back in, I don't know, 1400s, 1500s, got told to add the first 1 to 100 numbers up in his classroom, and he did it like back in a matter of like seconds, where everybody else is waiting on a long while. Teacher ends up beating him for fucking cheating or fucking being possessed. I don't remember. It might have been Euler or his fucking. It was someone, but he just recognized that this was true. He's like, I don't want to add this all up. I'm just gonna take advantage of this principle, and he just spit out the answer. So like, if we did, like I just said, n equals 1 to 100, the short formula of this is 100 times 101, which is 100 plus 1, over 2. 50 times 101 is 50/50. Yeah,
So is this kind of like a matrix?
no. Matrix has, it's a tic-tac-toe board. It's a grid. It's graph paper. I would just call this a formula. Will be what you do in Math 80. It's good for a lot of stuff in like computer science. Your TV screens or your computer screens are grids. Most of the shit when we need to do something that we don't know how to do in science, we convert everything into a fucking 3D grid, not 2D grid, but 3D grid. And it takes computers to do like the harder ones.
When would we use this formula in terms of like problems from like the past? What is
You're probably not going to have a lot of Riemann sum problems on a test. This is a tool to get to where we're going. Anyone need that up longer? Okay, so let's find the closed form of. Let's do the summation of k equals 5 to 15. Let's see, I want to make it one I know the answer to already. 2k minus 3. So closed form doesn't have summation in it anymore. So we need to use some of those formulas that we just had, which means I need to re-index to 1. To use the formulas. So I have k equals 5, and I want to re-index to, let's say, I equals 1. To do that, I want to make this look like k. So to look like k, I got to add 4 to it. And I get I plus 4 equals 5. So that I plus 4 equals k. And then I equals k minus 4.
Is there a reason you should? Next.
Yes, you do not have to, but it's easy to get confused in the transition. In fact, when I'm done, I'm going to go back to k. Let's re-index it, and then we can switch back to k. The reason why I don't say like k equals k minus 4, because listen to that out loud. If I wrote k equals k minus 4, I guarantee you more than one person in here is going to go, what the fuck is he doing? Right?
I'd be that person.
Right. And it's perfectly natural because it doesn't make any sense. It's a good question. Why the fuck did he write k equals k minus 4? So use a different letter or something else while you're re-indexing. If you particularly like a particular letter, switch back to it when you're done. So if I do that, when k equals 5, I equals 5 minus 4, which is 1, which is what we wanted. When k equals 15, I equals 15 minus 4, which is 11. So we are going to re-index to I equals 1 to 11. And k equaled I plus 4. This is 2i plus 8, and then minus 3. Now when I re-index, I'm going to switch back to k. Well, now when I clean up, I'm going to switch back to k.
we keep it like the one you have above it?
You can use it, keep it as I if you want. Should probably put this in parentheses because all of it is being added up. All right, so to get it into closed form, I got it down to, I re-indexed it. Now I need to get rid of the summation notation. So I'm gonna rewrite this as two different indices. I'm gonna have a K here. I'm gonna factor the two out. That was one of our theorems that we said we could do. So on both of these, n equals 11. I'm gonna rewrite this in terms of n, and then we'll put in n. This is 2 times n plus 1 over 2 plus 5 times n. And looks like the 2's cancel. When I plug the n in, I got 11 times 11 plus 1 plus 5 times 11. 11 times 12 is 132 plus 55 is 187. So here I just canceled out the 2's. And then I subbed in n equals 11. Good to go?
Where's the 5 times n?
This was a constant, and if I do, there's no k in it. So I'm just adding it up 11 times. We actually did this with earlier with 3. So it's one of the formulas, a constant in there, it ends up being the constant times n. As long as you start off your indexing at 1 or 0, the 0 wouldn't change it.
Use the formula for the first one.
You mean this too?
Yeah.
It's a multiplier times a k. We don't need to. If I'd left it in as the 2k, we wouldn't have,
I guess my question is like, why are we able to use the formula for the first term and not the second?
we did use a formula for the second one.
But you're able to bypass it, like you have to write it.
This is a constant, this is a k in terms of the index. They're two different formulas. This is the 2 to the k. This is splitting it up. Where's the. And I showed the C one earlier. We just have different formulas here. I'm not bypassing anything. I'm not sure where I'm losing you.
You got the closed form, like the N divided by 2, that thing going on.
That's the closed form of the constant one. Cause it's got an N.
Oh. Sure does,
Are we good now?
probably not. We can move on.
When we did it with the 3. 1 to 6. We ended up with 3 times 6. It's a different formula, yeah. It's the C. K equals 1 with a constant to the N is C times N. It's a different formula. Are you good now?
Think so.
Okay. All right, so where are we going with this? We actually talked about this before. In section 5.1, we got some curve. And we want to find the area underneath it. Let's say it starts at A and it goes to B. And we want this region right here. We want the area. We're going to break it up into n equal intervals. So this would be like A is x sub 0, this is x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, x sub 7 is B. And I've got 1, 2, 3, 4. Here I've got 7 regions. So in my picture, I have n equals 7. But in a generic form, we're just going to leave it as n. This length right here, that length is B minus A. So the width of each box, which we call delta X, is B minus A over N. We divide it by the number of boxes we made. And here we can approximate this stuff by making a bunch of rectangles. So length times width. Width is delta X. We got the width. The length is going to be the height. So what's the height? It's f of x, I'm going to say xk star times b minus a over n. The height of the rectangle, like we're going to pick, like for each interval, there's going to be like somewhere, we're going to call it xk star. We're going to come up and find the height of that there and do the function value there. And so we would add these up to get the area. We're gonna add them up. We have k equals 1 to n. F of x sub k star times that width, or delta x. So what does this f of x sub k thing look like? Well, we need to figure out what is x sub k. Then we can look at what f of x sub k star is. Yeah, Preston, sorry.
For k, why wouldn't we start at 0? Like k equals 1, like why wouldn't it be k equals?
Well, does it make sense to have a 0th rectangle? We're adding the rectangles, right? So this is the ith rectangle or the kth rectangle. That's a good question. Does that make sense? The 0th rectangle sounds silly. All right, so looks like people are done writing. I'm gonna rewrite this axis down here. Let's figure out what x sub k star is. So like if I rewrite this here, I'm gonna like stretch it out so I can write it a little bit better. That's a, and this was x0. And then we go a distance delta k, this or delta x this way. So this is a plus delta x. And then I go another delta x, and this is a plus 2 delta x. And I go another delta x this way, and this is a plus 3 delta x. And after n rectangles, it looks like I'm going to get up to this right one being a plus n delta x. So there's a couple options. Remember, we got this curve going on above it. So I'll only look at like this first box right here, just to demonstrate the curve. We could do the right endpoint and make the box like that with the right endpoint. And so I'm having my first rectangle is f of a plus delta x times delta x, plus the next one is, it'll go up to the next one is f of a plus 2 delta x times delta x. And we're going to go all the way up to f of a plus n delta x times delta x. So it looks like we're doing, this is like k equals 1, k equals 2, up to k equals n. This looks like x sub k whichever one I'm doing, like x sub 1, this is x sub 1 right here. So x sub k equals 1, this is a plus k delta x for my right endpoint. What do you think I'm going to get for the left endpoint? How does this change? So I'm no longer adding this point, I'm starting at that point for left. F of A times delta x plus f of A plus delta x times delta x. So this is my first box. My second box. My third box would be A plus 2 delta x. Delta x. That's my third box. So if I'm following a pattern here of what gets added to A plus like a multiplier times delta x, it looks like x sub k is A plus k minus 1 times delta x. That's left endpoint.
So left endpoint, so would it kind of be like a graph, since like going this way, it would be like negatives would be always be minusing one.
Yeah,
Okay,
it's like we're just doing -1, we're stepping left 1
yeah.
on each of these. So the nth one, we're doing the nth minus n minus 1. It's exactly what's going on. So we looked at doing something like this for a regular thing, but we didn't use these summation forms. Let's look at y equals 3x. Find the area under y equals 3x from 0 to 8. And let's use n equals 4. We're going to do this as an approximation. Then we'll find the exact area. Using limits. But I think we can start off right away and identify what the area is. If this is y equals 3x plus, or y equals 3x, when I get up to x equals 8, this is y equals 24. We are looking for the area of that triangle. Area equals base times 1/2 base times height. 1/2 4 times 24 is 48. Why did I say 4? It's 8, 1/2. I jumped the gun. I did 1/2 of 8 and wrote 4. So 4 times 24 is 96. 96 square units, whatever the units are. So that's the cheat method. Let's use left endpoints. Left endpoints, we'll use left endpoints. So let's see what delta x is. Delta x is b minus a over n, which is 8 minus 0. I'm going to leave it as over n for now, which is 8 over n. Because we're going to use that later on in that form. But for part A, n equals 4, or n equals 4, then delta x equals 8 over 4, which is 2. So we have the summation from k equals 1 to 4. We want to do f of the left endpoint is a plus k minus 1. K minus, I gotta leave k minus 1 in there. Because k is what we're going with. Delta x is 2. And then we multiply it times delta. So this is a plus k minus 1 delta x times delta x. So times another 2. And f is 3x. So 2 times 3 times a, which was 0. A equals 0. So I just have 3 times k minus 1 times the 2 in here. So that 2 is that 2. This 2 is that 2. And this 3 is the y equals 3x. Two times 3 is 6, times 2 is 12. 12 times k minus 1. So this is 12k minus 12. I got 12 times k equals 1 to 4 of k minus 12, or the summation k equals 1 to 4 of k. I'm sorry, of 12. We just split it up right there. This is going somewhere, I promise you. So we've got n equals 4. This one is that n times n plus 1 over 2.
It's off screen.
And this one is 12 times n. So 12 divided by 2 is 6. I say I wrote 14 there, n is 4. And then I got n is 4 times 4 plus 1 minus 12 times 4. This is 6 times 4 times 5. That's 120. And then minus 12 times 4 is 48. That's 72 square units. So it underestimated. Yeah, that's,
And this is only the approximate area.
yeah. We use left endpoints. So with the picture, like our first rectangle is actually 0. Our second rectangle is that. So we can see that we're less than the actual area. I hit the menu button, sorry. We can see that we're less than the actual area. But if we use an infinite number of parts, like to make the width of each thing super fucking infinitely small, do n going to infinity, all of that shit we lost in this picture goes away. Like if n's 1,000, we lose very little. When n goes to infinity, we don't lose anything. So that's what we're gonna do for part B. Let's look at doing like the exact area using limits. So the exact area should be if delta x goes to 0, n goes to infinity to make that happen. Because delta x is b minus a over n. And the only way to make b minus a is constant numbers. The only way to make this get to like a 0 width or something super small is make n get super large. So that's what we're going to do. We're going to do the limit as n goes to infinity of f of x sub k star delta x. Let's apply that here. We had delta x was 8 over n. If I come up here and like see what we had this part right here was the f of x. This was my delta x. Because we're going to do a, which is 0, 2 times k minus 1. We're plugging 2 times k minus 1 into 3x. So we're going to have the limit as n goes to infinity. That's 6 times k minus 1 times 8 over n. Oh wait, nope, no, back up. Because that 2 was also 8 over n. Let's go back to the beginning. Limit as n goes to infinity. F of a plus k minus 1 times delta x. That's the full equation. Jumped the gun here. I went a little hasty. We got delta x here. We know a equals 0 because the boundaries were 0 to 8. Does that make sense? Get rid of what I said a little bit ago. I tried to shorthand it here to speed it up, and there's no speeding this up. We got to do the long form here. So this is the limit as n goes to infinity of f. A is 0. I've got K minus 1 times 8 over n. That's in my big function. Times 8 over n. And the f part just makes this 3 times k minus 1 times 8 over n, and then another 8 over n. I've got 3 times 64 is 192 times k minus 1 over n squared. And this is a summation still. I dropped my summation notation. Son of a bitch. So if I break that up, I've got n as a constant with respect to k. So I've got 192 over n summation of k equals 1 to n of k minus 192 over n of k equals 1 to n. Well, it looks like I factor everything out, so 1. And that's an n squared on bottom. There was 2 n's. Not so simple now, is it? It's a fucking pain in the ass. We went from fucking easy to a pain in the ass really quickly, right? All right, so we still got our limit here. We've got 192 over n squared. The summation from k equals 1 to n was n times n plus 1 over 2. And then we have minus 192 over n squared. K equals 1 to n of 1 is just 1 times n, or n. Pause, make sure you catch up here. This would have been easier with right endpoints. I can pull the 192 out. That's a property of limits. This is n squared over 2n squared. I'm breaking this up into a bunch of fractions here. Plus n times 1 is n over 2n squared minus n over n squared. Yeah,
You get 192.
3 times 8 times 8.
Oh, okay. I didn't see that.
There was a catch coming. You knew it was coming, Isaac. Thankfully, we're gonna be doing integrals most of the way. If you go into pure mathematics, you'll be dealing with this a lot. This is called the Riemann sum. We're gonna Riemann sum, and I'm gonna hit it more on Tuesday. I had wanted to get through 2 sections today, but this section like is a pain in the ass. And I want to make sure you understand how it works because it's the principle of how we do integrals. All right, so we shrinky dink. Cancel shit out. This is just 1/2. This is 1/2n minus 1/n. Remembering to write the limit and the summation notation is a pain in the ass, but you should do it because otherwise it gets confusing and I like lost what I was doing. I had to go back and backfill it in. I made a mistake. All right, so when n goes to infinity, if there's an n in the denominator and not in the top, these go to 0. So this goes to 192 times 1/2, which is 96. Which is what we got doing 1/2 base times height. You have a question?
So when we did the approximate area, did we just do that just to like, just the approximate area, that's your.
Yeah, to show what happens.
I was thinking like we were gonna use the approximate area to need to find the actual area.
As n gets larger, that approximate area gets closer and closer to it,
Or 96.
to 96. So we only did n equals 4. If we did like n equals 20, we should get a lot closer to 96. And as n skyrockets. All right, so that was doing the area under the curve. What if the curve goes underneath the axis though? That's a region, that's a region, that's a region. So if this is like area 1, area 2, area 3, the net signed area we're going to add A1, we're going to subtract A2, and we'll add A3. And the reason why we're going to subtract A2 is f of x is less than 0 here. So we're adding a negative, like the height is negative times the width is positive. We're still basically adding the area, but the area is now negative. Yeah,
It doesn't exist, is that what you're saying?
no, it exists, we're subtracting. It's gonna take away from the total value. So if you had something where it was like if we did y equals x. And I did from -3 to +3. Let's make it 6 and -6. The height here is 6, so that's 6, 6. And this is -6, -6. The rectangle, this is gonna have positive area, 1/2 base is 6 times height is 6. But this region has 1/2 base, which is 6. But the height is -6 here. It's going down. So you'll see, like if this is A1 and this is A2, A1 is -18. A2 is +18. And the net signed area is 0. They cancel each other out. Does that make sense? Like this is 1/2 base times height. I did 1/2 base times height on each of them. But the height here is -6. And the height over here is +6. That's net signed area. This holds true if you do y equals x. Or y equals like any odd function really. And you go from -n to n. The area is going to be 0. Until you say limit as n goes to infinity. Then we can't assume it's 0. Which is irritating as fuck. I got madder than shit when my calculus teacher told me this. I know who it was. It was Christine King. She teaches here. And I argued with her. I'm like, why does it work from -1 to 1, -100 to 100, -1 billion to a +1 billion? And all of a sudden we just say infinity and that principle goes away and it's no longer 0. And she says, because when you have infinities involved, you can't assume shit. And I didn't like that answer, and I still don't like that answer, but I don't have anything better for you. So I realize that's a frustrating statement. That's net signed area. We can have negative areas when f is the curve goes below the graph. It's canceling out positive areas. Now, if you picture something like income, like there's money here, and you're counting up like how much money you earned, this is definitely counts as a loss. You lost money. So understanding, like seeing, okay, we had money here, we lost money here, seeing how they cancel each other out makes sense when you apply them to applications.
Wait, so what happens when the negative area is greater than all the positives?
You end up with a negative answer.
Then that'd be like a fake answer. It would like just like not exist. So,
It's called, that's why it's called the net signed area.
uh,
We don't call it area anymore as soon as we have shit going below the graph. Because you're right, area needs to be greater than 0. So we throw in the special label net signed. And now this is like translating how else we can use this. Because this is going to switch to integrals real quickly. And now we're just going to have, we have to throw in A and B for our integrals. And we didn't have that in our other ones. But this allows us to do it and use the net value. All right, it's 10 o'clock. Have a good weekend. Next week is only one day. Wednesday, Thursday, well, it's Thanksgiving. Wednesday is off also. So if you have classes on Wednesday, there's no class. All right. GTFO. Have a good one.